So I would like to show you the proof that for a given perimeter, the square maximizes the area of a rectangle. So let's look at a rectangle with side lengths x and y. The perimeter of the rectangle is given by 2x plus 2y. We're going to assume the perimeter is fixed. The area of the rectangle is given by the product of the sides, x times y. So we want to find the maximum of the area with a fixed perimeter. Here we have the area as a function of two variables, x and y, but we can use the perimeter equation to eliminate y. So if we use the perimeter equation, we get y is equal to p minus 2x divided by 2, and we substitute into the area formula. So the area is equal to x times p minus 2x divided by 2, and that becomes p over 2 x minus, the 2's cancel, and we have minus x squared. So in order to maximize the area then, we want to set the derivative of the area with respect to the single variable x here to 0. So to maximize the area, we calculate the derivative. dA dx is equal to p over 2 minus 2x, and we set that equal to 0. The value of x here, we can solve for x. So 2x equals p over 2. So x is equal to p over 4. So one side is a quarter of the perimeter. So that means the other side also has to be a quarter of the perimeter. So that the 2x plus 2y is equal to p. And what that means then is x equals y, which is a square. You may ask, how do I know that that's a maximum? Well, you know that if this rectangle becomes extremely thin, the area goes to 0. So the critical point then in the middle of this rectangle becoming extremely long or extremely tall has to be a maximum. Let me summarize. So this is our first use of the derivative to find the maximum of a physical problem. What we're maximizing here is the area holding the perimeter fixed. The way to do that is to write the area as a function of a single variable and set the derivative equal to 0. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.